In 1972, a French physicist noticed that a shipment of uranium ore was missing something. The sample had come from a mine in the West African country of Gabon, and when it was run through the standard isotope analysis, a tiny fraction of one isotope, uranium-235, was lower than it should have been. The difference was almost nothing, 200 parts per million. On paper, an error. In reality, the opening of one of the strangest chapters in the history of geology, because the only way for that isotope to be missing was for it to have already been used, burned, consumed in the exact way a nuclear reactor consumes fuel. The ore was not ore. It was spent fuel, and it was about 2 billion years old. The site is called Oklo. It is real. It is documented. It sits in the Franceville Basin, in the southeastern corner of Gabon, and for more than 5 decades, scientists have been studying it and arguing about what it implies. There is no fringe speculation required here. The International Atomic Energy Agency has published technical reports on it. French and Gabonese government scientists have cataloged the rock layers. American national laboratories have weighed in. The consensus, at least in the narrow sense, is clear. Oklo hosted a series of natural nuclear fission reactions approximately 1.7 to 2 billion years ago. Groundwater, uranium-rich sediment, and the right geometry produced a slow, self-sustaining chain reaction in the Earth's crust, cycling on and off for possibly hundreds of thousands of years. The reactor zones, when they were finally excavated, contained the chemical fingerprints of fission products: xenon, neodymium, plutonium daughters. Things that are not supposed to occur naturally, but did. That is the accepted science. And most science documentaries stop there. The part that does not get as much attention is what Oklo does not explain. Because once you accept that a nuclear reactor can form by itself, deep in the ground, from nothing more than water and the right kind of rock, the next question becomes uncomfortable. Did it only happen once? Did it only happen in Gabon? And if it happened more than once, what else is still buried? The reason Oklo was able to run at all comes down to a specific window in Earth's history. Uranium has 2 main isotopes that occur in nature: U-238, which makes up most of what you find, and U-235, which is the fissile part, the part that can sustain a chain reaction if you get enough of it in one place. Today, U-235 accounts for less than 1% of natural uranium. At that concentration, you cannot run a reactor without enriching the fuel artificially. But U-235 decays faster than U-238. That means billions of years ago, the natural percentage was higher. Around 2 billion years back, it was above 3%, roughly the enrichment level of modern commercial reactor fuel. In that window, if you had uranium ore, water to act as a neutron moderator, and a geometry that concentrated the material, you could, in principle, start a reaction without any human intervention at all. That window closed a long time ago. The U-235 has decayed too much. A new natural reactor cannot form today, but during that window, the conditions existed for at least a few 100 million years. And that raises the obvious question: why would it only have happened in one place? The honest answer is that it probably did not. Oklo is just the one we found. It was found because a piece of its spent fuel made it into a commercial uranium supply chain, and a French physicist happened to notice an isotope ratio that was off by a fraction of a percent. If that shipment had gone to a less careful lab, or if the sample had been taken from a slightly different vein, the discovery might have been missed entirely. Geologists have since identified around 17 distinct reactor zones clustered at the Oklo site, plus a related site at Bangom nearby. All of them are natural. All of them operated in the same deep past. And all of them survived, which is where the truly modern part of the investigation begins. Because in the last few years, machine learning models trained on satellite geochemistry, ground-penetrating radar, and rare earth element maps have started looking at other regions of the planet where the underlying geology resembles the Oklo Basin, West Africa, parts of northern Australia, sections of the Canadian Shield, old cratons, the most ancient stable pieces of continental crust, where uranium-bearing sandstones have sat undisturbed for billions of years. The models are not claiming to find reactors directly. What they are flagging are signatures, trace patterns of fission-derived isotopes, unusual concentrations of neodymium and samarium that suggest the rocks have seen neutron flux, areas where xenon gas, trapped in microscopic bubbles within ancient mineral, grains shows isotope ratios that do not occur in normal background rock. Several of these signatures are real. Several have already been confirmed in the peer-reviewed literature. The Cigar Lake deposit in Canada, for instance, has long been studied for evidence of ancient criticality. Some Australian uranium deposits show chemical quirks that researchers have attributed to past fission-like events. None of these have yet been proven to be full reactors in the Oklo sense, but the patterns keep appearing, quietly, in technical papers, in geology conferences, in the sort of footnotes that never make the evening news. Now it gets more interesting, because a reactor that ran for hundreds of thousands of years in a geologically active region leaves more than just spent fuel. It leaves heat, it leaves chemistry, it leaves transformed rock. And when researchers look at the Oklo site today, they find something that quietly revolutionizes our understanding of nuclear waste storage. Almost all of the radioactive byproducts from those ancient reactions stayed in place for 2 billion years, through continental drift, glaciation, erosion, and countless groundwater cycles. The plutonium that the reactor produced did not migrate. The cesium did not migrate. The strontium did not migrate. The rock held it, quietly, completely, without any human engineering. This has implications that go far beyond an interesting rock formation in Gabon. If nature can contain nuclear waste in sandstone and clay for 2 billion years, then the modern problem of storing spent fuel from our own reactors may be a lot more solvable than political debate suggests. Scientists who specialize in deep geological repositories have pointed to Oklo as a natural experiment, a proof of concept that, under the right conditions, hot radioactive material can be safely sealed in the crust without leaking into the biosphere. That, by itself, is a major finding. It does not need any exotic interpretation to matter. But the more speculative questions keep coming back. Because Oklo is old. Not just old in human terms. Old in biological terms. 2 billion years ago is before multicellular life, before complex organisms, before most of what we recognize as Earth's living history. When Oklo was running, the atmosphere was still transitioning from a low oxygen state. The continents were arranged differently. The day was shorter. The planet, in effect, was another world. And on that other world, deep in what is now African rock, nuclear reactions were quietly burning for stretches of time longer than some species have existed. Not everyone is convinced the story is as tidy as the textbooks make it sound. Dr. René Calder, a geochemist who has argued for revisiting some of the early isotope analyses, has publicly suggested that certain aspects of the Oklo data may not fit the simplest natural reactor model. Her position, to be clear, is not that the reactors are artificial. It is that some of the chemical migration patterns look more complicated than a purely static, undisturbed reactor would produce, and that the site may have experienced multiple pulses of activity rather than a single long burn. That nuance matters. It suggests that even the most conservative reading of Oklo may still be missing part of what happened there. The online conversation, meanwhile, has gone further. Some writers have pointed to the age of the reactors and asked whether the natural formation story is really as airtight as it seems. They note that the geometry of the reactor zones, the spatial arrangement of the fissile material, the placement of the water pathways, the presence of clay layers that happen to act as neutron reflectors, resembles, at least loosely, the design of a crude human-built reactor. The counter, which is well argued by the mainstream geology community, is that this is a classic case of seeing design where there is only selection. The conditions at Oklo were not chosen. They were what happened to survive. Every other place on Earth where the conditions did not line up, nothing happened. We only see the one that worked. That is how natural experiments always look in hindsight. Still, it is worth pausing on the sheer scale of what the evidence does support. A nuclear reactor, formed without any intelligent design, running for possibly hundreds of thousands of years, in 15 or more separate zones, containing its own waste for 2 billion years, discovered only because a French lab did the isotope chemistry on a routine uranium shipment. That is an astonishing fact. You do not need to exaggerate it. You just need to sit with it. What the newer AI-driven surveys seem to be suggesting is that Oklo may not be the only ancient site where this happened. It is the only one we have excavated so far. But in remote regions of the planet, where the old cratons still preserve the rocks of that era, there are hints, signatures, elevated daughter isotopes, unusual heat flow histories, rock that has seen something unusual. Whether any of those sites will turn out to be confirmed ancient reactors is an open question. Researchers are cautious because the bar of proof is high and the data is easy to misread. But the fact that the models keep flagging these regions is a data point in itself. A deeper question is what this tells us about the universe, not just the Earth. If a natural nuclear reactor can assemble itself in the crust of a young planet, then the conditions for such reactions likely repeat elsewhere. Other rocky worlds with similar geochemistry and similar water cycles could, in their own early histories, have hosted their own Oklos. Some of them may still be running, under ice in the crusts of distant moons, or in worlds we have not yet imaged. The possibility is not proven, but it is no longer absurd. The universe, it turns out, is perfectly capable of building a reactor on its own. We only needed one example to know that was true. Back on Earth, the Gabonese government declared Oklo a national scientific site. Access has been restricted for decades. Most of the physical reactor zones have been mined out. The uranium was, after all, the reason anyone went there in the first place, and the remaining material sits under protection. Some of the spent fuel from those prehistoric reactions has been preserved in research collections around the world. You can stand in certain labs and look at a rock. That was part of a working nuclear reactor when the most advanced life on Earth was still single-celled. For anyone who thinks the strange parts of the world have all been catalogued, Oklo is a quiet, permanent counter-argument. It does not require a lost civilization. It does not require anything supernatural. It only requires that nature, given enough time and the right ingredients, can do things we thought required us. And the lingering question is not whether a natural reactor is possible. We know it is. The question is how many of them are still sitting, unnoticed, in the deep rock of old continents. How many signals the current generation of models is going to flag in the next few years. How many more Oklos the planet has been keeping quiet about. For now, the safest thing to say is also the most unsettling. The Earth has built reactors before, without us, without witnesses. The only reason we know is because someone, half a century ago, checked a number that almost did not get checked at all. If that is the story the confirmed science tells, it is worth asking what the confirmed science may still be missing. To really appreciate how improbable the discovery was, it helps to know a bit about Francis Perrin, the French physicist whose name is attached to the original Oklo analysis. Perrin was not looking for a prehistoric reactor when he noticed the anomaly. He was running standard quality checks on uranium feedstock at the Pierre-Latte enrichment facility. The sample, processed from ore shipped out of the Munana mine in Gabon, came back with a U-235 fraction of 0.7171% instead of the expected 0.7202%. That is a difference of about 3 parts per thousand. In any other context, it would have been attributed to measurement drift and set aside. Perrin did not set it aside. He traced the anomaly back through the supply chain, sampled different parts of the ore body, and found that the depletion was not uniform. It was concentrated in specific zones. Those zones turned out to be the reactors. The entire discovery rests on one physicist noticing a fraction of a fraction and taking the time to explain it. That is the kind of detail that gets easily lost in the bigger story. Oklo was not announced in a blaze of publicity. It was published quietly in French scientific journals in 1972, and the international community took a few years to fully accept the finding. There was, at first, a reasonable skepticism. Some researchers suggested that the isotope depletion could be explained by preferential leaching, the idea that U-235 might have been selectively carried away by groundwater over geologic time. That hypothesis fell apart when the fission product signatures were confirmed. You cannot leach xenon-133 decay daughters. You cannot leach a specific isotope ratio of neodymium that only appears after neutron bombardment. The rocks were not just depleted. They were chemically transformed in ways that only a working reactor could produce. The deeper the analysis went, the more remarkable the picture became. Researchers were able to estimate the operating parameters of the ancient reactor. The average power output across the Oklo zones is believed to have been around 100 kilowatts, about the heat output of a small industrial furnace. Low by modern reactor standards, but steady. The reactions did not run continuously. They appear to have pulsed in cycles of roughly 30 minutes on, 2.5 hours off. That pulsing came from the moderator. Water seeped into the uranium-rich sandstone, slowed the neutrons enough to sustain fission, heated up, turned to steam, and escaped. Without water, the reaction stopped. Groundwater refilled the zone. The cycle began again, for hundreds of thousands of years. A geologic metronome. This detail, the self-regulating cycle, is part of what has kept scientists returning to Oklo for decades. It is not a runaway event. It is a reactor that passively throttled itself, staying within a narrow range of activity for an astonishing length of time. There is nothing like it in the artificial reactor designs of the 20th century. Modern nuclear engineers have looked at the Oklo mechanism with genuine admiration, and some of the concepts for next-generation passive safety reactors draw explicitly on lessons from the Gabonese site. The planet, in a sense, solved a reactor engineering problem 2 billion years before humans began working on it. There is also a less discussed aspect of Oklo that matters for the broader question. During the operation of the reactors, they produced plutonium, specifically plutonium-239, which is formed when U-238 absorbs a neutron and then decays. Plutonium-239 is the main fissile isotope used in nuclear weapons, and it is the main product of modern breeder reactors. At Oklo, it was produced in measurable quantities, and then it sat in the rock, and it decayed. Today, no plutonium remains. It has a half-life of about 24,000 years, which is long on human scales and trivial on geologic ones. But the decay chain left fingerprints, specifically an enrichment in uranium-235 relative to what decay alone would predict, because plutonium-239 decays into U-235. This is how we know the reactor bred plutonium. The chain of inference is long, but it is solid. What this tells us in practical terms is that the ancient reactor went through every stage of a modern fuel cycle: initiation, criticality, power generation, fuel depletion, waste production, waste containment, decay. All of it in sandstone, in darkness, without anyone watching. For the people who worry about the long-term storage of modern nuclear waste, Oklo is the closest thing to a pre-run experiment that the planet has provided. The answer it gives is encouraging. Waste can stay put for a very long time. None of this changes the central strangeness. A natural reactor should be a rare event, perhaps even a one-of-a-kind event. Oklo is not one event, it is 17. The probability of the right conditions assembling once is already low. The probability of them assembling 17 times in the same general neighborhood is lower still. Either the conditions were not as rare as we initially thought, or the site had some property that made it unusually favorable. Some geologists suspect the latter, that the Franceville Basin, during the specific window when U-235 was abundant enough, had exactly the mix of sandstone, clay, and groundwater flow to repeatedly produce critical geometries. Others suspect the former and are actively hunting for more sites. The AI-driven surveys are one part of that hunt. Another part involves re-examining old core samples. Mining companies around the world have collected millions of core samples over the past century, and most of them have been filed away after being checked for the obvious commercial elements. Some researchers are now going back through those archives, running modern isotope analysis on samples that were originally examined only for basic uranium content. The work is slow. It is not glamorous, but it has started to produce hits. A core from northern Saskatchewan, stored for decades in a university warehouse, turned out to show isotope ratios consistent with past neutron flux. A set of samples from a remote region of the Pilbara in Australia flagged similarly. None of these are confirmed reactors yet. They are candidates. The pattern, though, is becoming hard to dismiss. In parallel, theoretical modeling has started to predict where new sites might be found. The models take as inputs the age of the rock, the uranium grade, the local hydrology, and the mineral context. When those variables line up within certain narrow windows, the models suggest that a natural reactor is possible, given enough time. The outputs highlight regions of Earth's ancient crust that have not been surveyed for this purpose before. Over the coming decade, field teams may begin to ground truth those predictions. If even one of them produces a second confirmed ancient reactor, it will force a significant rethink of how common these events actually were. It is also worth pausing on what Oklo teaches us about the assumptions we carry into science. For most of the 20th century, nuclear fission was understood as a human achievement. The Manhattan Project, the post-war reactors, the hard-won engineering to confine and sustain a chain reaction. Oklo shows that fission is not a human trick. It is a natural phenomenon that required specific conditions to occur, and when those conditions were present, it did occur. Humans did not invent it. We discovered it. And we discovered it, in a sense, twice. Once in the labs of the 1940s and once in the rocks of Gabon. For now, the safest thing to say is also the most unsettling. The Earth has built reactors before. Without us, without witnesses. The only reason we know is because someone, half a century ago, checked a number that almost did not get checked at all. If that is the story the confirmed science tells, it is worth asking what the confirmed science may still be missing, and whether the next Oklo is waiting in a core sample drawer, in a satellite image, in the kind of number that almost nobody bothers to check twice.